Scientists at Penn have invented a new method of producing filtration membranes that are much more efficient than what's currently available.
The technology that we are developing in my lab is membrane technology. You can think of a colander that's used to drain pasta. It's a membrane that allows the passage of water, but doesn't allow pasta to pass through it. The way in which that works is that you have holes in the colander or holes in the sieve, which allow certain things to go through, in this case water, the liquid, but doesn't allow certain other things to go through. Membranes, of course, are present all around us, and the most obvious examples come from the field of water purification. Most of today's membranes suffer from something called permeability selectivity trade-off.
This means that if you want to make the membrane more permeable, for example, to filter more water at a faster speed, you have to make it less selective, which gives you water that is less pure. But if you need a more selective membrane for purer water, the speed is slowed down by a lower permeability. This trade-off is primarily caused by the process used today for manufacturing membranes, which creates holes that are many different sizes.
The membranes that we've developed in my lab make use of structures that are all the same size. So they are structures that are produced by a process called Selfassembly, and it's this size uniformity that sets our membranes apart from conventionally prepared membranes. So there's a very thin layer on top, which is actually our material. This is where the innovation lies. So at 100 or 200 nanometers thick, we're talking about 1,000 times smaller than the thickness of a human hair. That's where all the magic happens. That's the so-called selective layer. And so we focused a lot in the lab on proof of concept experiments that demonstrate the ability of our membranes to remove dissolved solutes in water, dye solutions where the color has been removed, whiskey where we've removed the color of the whiskey. You can think of things like point of use water filtration, treatment of wastewaters coming out of industrial facilities, water softening for household use, pervaporation or membrane distillation, which are processes that are used for the production of milk and orange juice and things of this nature. We also have two other applications that we've been developing.
The first of these is a membrane that is compatible with organic solvents like ethanol, hexane, toluene, and THF, which tend to degrade typical membranes.
So if you can develop a membrane that is durable enough to withstand passage of organic solvents through it, then there's a whole range of applications for industrial separations that you can address. And one final application that we've been looking at is the rejection of chemical warfare agents, but the passage of water vapor and oxygen and useful gases through membranes as a material for soldier protection. For me, it's exciting because we get to put our science to the test. Can you make a viable, practically useful membrane for existing separation processes and for yet to be implemented other applications using these materials that we're so excited about? That's why the Y Prize for me is exciting.